Morning, my dear students. The last class we have understood the various parts of the syllabus what we are going to study with respect to model number 1 and model number 2. And now come to the model number 1. The first part of that we are going to study how to design a combined footing. Hence, what is a footing? We shall try to understand. It is the lowest part of a structure which is in direct contact with the soil and transfer the load to the soil beneath. Hence, this footing will transfer vertical loads, horizontal loads, moments acting on the column, and also all the kinds of, it may be a wind load also, to the soil. And this has to transmit this load, the structure, to an sufficient area of the soil. Hence, with this, we in the fifth semester, to find the area of the footing, what did we do? To find length and the breadth of footing, we took area of the footing is equal to total load acting on the column divided by safe bearing capacity of the soil. Hence, we found out the length of the footing as well as the breadth. The footing. But if this length and the breadth of footing is more, then when the two footing will overlap, we go with a combined footing, where we have two columns. The common slab, footing slab, is called as a combined footing. Under this is called a definition of a combined footing, where to support the load of two or more adjacent columns. When do you come across this combined footing? Whenever the columns are nearer to each other, so that the isolated footing will overlap, or when the bearing capacity of the soil is very low here and the area of the footing is more required for engineering footing, then we go with a combined footing. Or if by chance one of the column is very close to the property line and the center of gravity of the column will not coincide, we go with the combined footing. So hence there are various types: slab type, slab beam type. So hence today we shall talk about the design of a slab type combined footing. So here it may be a rectangle or trapezoidal. So what are the data required for the combined footing? Hence we require the size of the column given the problem, the loads acting on the two columns, we can call it WA and WB, center to center distance, and safe bearing capacity of soil, how much is going to bear, period of the concrete as well as period of steel will be given the problem. The first step is to find out the size of the combined footing. Later you have to do something called as shape force diagram and bearing moment diagram, that is called analysis part, and later we do the design of steel, that is design of the depth of slab as well as steel. So there are two types of steel. One is called Lawrence steel. The steel perpendicular Lawrence reinforcement is called as transverse reinforcement, and finally we have to give a structural detailing of this combined footing. And the first step, as we discussed, that is to fix up the size of combined footing. To find the size of footing is equal to, the fifth semester we have understood that the total load acting on the footing divided by safe bearing capacity of soil will give us the area of footing. Also, instead of one column, we take total load on the columns plus self weight of the footing, which is considered 10% total load of the columns divided by safe bearing capacity of soil. With that, we do the structural analysis of the for shear force and bearing diagram. Now we shall understand a numerical problem. Here is problem: design a combined footing for two RC columns A and B separated by distance 4 meters center to center, and the column A is 400 mm square, which carries a load of 800 kilonewton, and the column B is 500 mm square column and carries a load of 1200 kilonewton, and safe bearing capacity of soil is 180 kilonewton per meter square, and the column A is 600 mm from the property line. Use M25 and FE4 and 5. So hence please make a note of this problem where the data is given that two columns of size 400 mm and 500 mm and it is having unequal load. One is 800, other one is 1200. And the same bearing capacity of the soil is 180 and the material used is M25 Fe4 and 5. Hence, based on this, the first step is to find the dimension of the footing. First step is to find out total column load, that is 800 plus 1200 is equal to 2000. As I told you that we have to take the self weight of the footing in the problem as 10% of the column load. Hence, I have taken here in this problem self of the footing is equal to 10% of the column load is equal to 200 kilonewton. Hence, the total load acting on the footing is equal to 2200 kilonewton I'm going to get. Hence, with that idea, we calculate the area of footing is equal to 2200 divided by same bearing capacity soil. As this is not multiplied by partial safety factor in the numerator also, please do not multiply by the partial safety factor. Hence, with that regard, I would get an area of 12.22 meters square. So now, as the column dimension is given as 4 meters center to center, that means to say I have in this problem the distance from center to center is 4 meters in the problem is given in the problem as 4 meters center to center, and each column load is 800 and 1200. Hence, one is 800, 1200. This is 4 meter. And in the problem already, please go through that. He is given that one of the column A is 600 mm from the property line. This is the data given. Hence, from here to the property line is 0.6. Hence, 0.6 plus 4 meter and P2 projection should be found out. Now, this load is 800. This load is 1200. If both the loads were equal, let me to say 800 and 800, then the center of gravity of the loads would have acted resultant exact center. But now it is unequal load. So hence you have to proportion the footing such that the resultant will act at the center. So that's what is written here. The projections of P1 and P2 should be such that the center of the gravity of the column load should coincide with the center of gravity of footing. That means to say, I take a section here somewhere the centroid is acting at a distance of L by 2, hence 0.6 plus x bar. So this is from here to here is x bar, from here to here is x bar. Hence, to find x bar, we have learned in the second sem engineering mechanics to find the x bar, taking a reference axis, the centroid is equal to, when I have a force P1 is 800 and this is 1200. So we do the centroid formula is equal to x bar is equal to A1 x1 plus A2 x2 divided by A1 plus x2. So hence here I have written 0.6 plus x bar is equal to L by 2, where x bar is the centroid distance. And what is this I have to write? This is nothing but the force acting on this column A1 into x1. The reference axis here only x1 is 0. And you have here A2 into x2 is 4 meter divided by the total load, that is 800 plus the 1200. So hence with that concept, 0.6 is the projection from here to here plus x bar is 800 and the reference axis is the same line of reference, hence it is 0 plus 1200 into 4 meter divided by the 800 plus 1200 is equal to L by 2. So now you please take out your calculators and try to work out. You would get the L is equal to 6 meters. As we know that L into B is equal to 12.22 meters square. Hence L into B is equal to 12.22 meters square. Now here I got L is equal to 6 meters. I put 6 meters to B. I get 2.03. Round off for 2.1 meter. Provide a little more. But don't change the length because we already taken the consideration L by 2 here. So hence provide 6 into 2.1 meter. But how do I find out P2? So we know that P1, that is 0.6 meter plus 4 meter plus P2 is equal to 6 meter. So that's what is written here. That is P1 plus 4 plus P2 is equal to 6. So substitute the value of P1. So you can find out the P2 you would get as 1.4 meter. That means to say P1 and 4, you please take out this side. So 6 minus 0.6 minus 4 is equal to 1.4. So this is what we get. So once you get this, we understood in the last class that to find the area of the footing step-by-step procedure, the structure analysis, that is total load WA plus WB plus Q0 we have worked out, and we have taken AF into LF into vertical flange, what I explained just now, and we found out the X bar here and the projections, and later we have to find out the upward pressure. And this is with respect to the ultimate load method or limit state method. So hence in this problem, to find the upward pressure, only the column load, that is what load is occurring, divided by area of the footing L into B. So hence you have the column load 2000 by the footing is 6 into 2.1, you get as 158.73 kilonewton per meter square. So this is what in the first step you will get the dimensions of the footing, proportions of the footing, and later the upward pressure in the problem. Hence, after this, the step number 2 is structural analysis, where you have to calculate the Bremen diagram and shear force diagram. Hence, I had two column loads 800, 1200. This is upward pressure 158.73. So now observe the plan view. This is 158.73. So this is the cross section. So hence 50% of the load comes on this, as well as 50% of the load comes on this. So 50% plus 50% is nothing but 100%. So I have to multiply into the breadth of the footing acting on the center line of this. Hence in this problem, it is multiplied 158.73 into the breadth of the footing what you thought or what you have taken, 2.1 meter is equal to 333.33 kilonewton per meter. So this is the loading diagram of the combined footing. So now let us try to understand now how do we calculate the shear force diagram. So hence we have learned in the third semester the shear force diagram, upward forces are positive and the shear force at this point is equal to 0. At this point, how do we calculate? Take out your calculators. 333.33 into 0.6 W2L, I will get 200. So at this same point, you have 800 downward force, hence 200 minus 800, I will get as 600 here. So now 600, this is minus 600, this is acting upwards, so hence it is taken as positive. Hence minus 600 plus 333.33 into, from the distance from here to here is 4 meters. When you substitute this value, you would get as, please check out, get 733.33 kilonewton per meter. Now 733.33 minus 1200, you will get 466.67 as. Now to get here, you should get 0. You say minus 466.67 plus 333.33 plus what would be the P2 projection? We have already calculated here. There is 1.4 meter. So hence 466.67 minus 333.633 into the 2 projection 1.4 meter. When you do this, you will get 0. So hence this is what the shapefold diagram calculation we're going to get. So now there is somewhere, then later we have to calculate the position of or the maximum bending moment diagram. So hence this is the cantilever part. So here at this point, if I take a section, it will be the bending moment at this point will be, this is making a sagging bending moment, upward movement. So hence sagging moment is positive. This is negative, positive. Then say, what do we do here? 333.33 into 0.6 into 0.6 divide by 2. I will get as 60 kilonewton meter. The same way, when I keep my section at this point, 333.33 into 1.4 into 1.4 divided by 2, we get as 326.67 kilonewton meter. Hence, the step is to work out where this zero shapefold occurs. So hence, you can work out by similar triangles. So it has been worked out as 1.8 meter and 2.2 meters. So now once you get this position, at this point where you have zero shear force, you'll be having the maximum bending moment. Keep a section here at 1.8 meters. So take your section 1.8 meters, work out that is 0.6 plus 1.8 into 333.33 into the this point plus 1.8 square minus 800 into that distance 1.8, you will get as 480 kilonewton meter. This is the way you draw the bending moment diagram. So you have done the shapefold diagram and the bending moment diagram. Hence, after this, we have to know where we have to provide the steel reinforcement. So based on bending moment diagram, the next analysis is to draw the elastic curve of the beam or the slab. So here you are seeing sagging bending moment, hogging bending moment, sagging. Hence I have written sagging, hogging and sagging. So hence with this concept, here you have sagging bending moment. Steel should be provided in the bottom. Here the steel should be provided in the top because tension will be here. Like that, you have an here the sagging moment, that is called as tension reinforcement, should be provided here because this fiber is subject to tension. So this is the flow chart, and later is the design. This we shall discuss in the next class.